Welcome! In this session, we'll tackle an engaging problem, problem number 222, count complete tree nodes. Together, we'll explore different approaches to solve this problem efficiently. Let's dive in. In this problem, you're given the root of a complete binary tree, and your goal is to determine the total number of nodes in the tree. Now, a complete binary tree has a specific structure. Every level of the tree, except possibly the last, is completely filled with nodes. If the last level isn't fully filled, then all its nodes are aligned as far to the left as possible. This means that depending on the height of the tree, the last level can have anywhere from 1 to 2 to the power of h nodes. The input will be provided as the root of the tree, represented by a tree node object. Your task is to return an integer that represents the total number of nodes in this binary tree. Let's look at some examples to better understand the problem. In the first example, the tree has 6 nodes in total. The root node, 1, has 2 children, 2 and 3. Node 2 has 2 more children, 4 and 5, while node 3 has only 1 child, 6. Because this is a complete binary tree, all levels are completely filled except for the last one, which is filled from the left. Therefore, the output is 6. In the second example, the tree has only 2 nodes. The root, which is 1, and a single child, 2. Here, the tree is also complete since the last level is filled as far left as possible. The output is 2. In the third example, the tree consists of only the root node, which is 1. Since there are no other nodes, the output is simply 1. Now let's discuss the constraints and edge cases for this problem. The number of nodes in the tree can range from 0 to just under 2.1 billion. As the upper limit is 2 to the power of 31 minus 1. Importantly, the tree is guaranteed to be a complete binary tree, so you can rely on that property while solving the problem. For edge cases, if the tree is empty, meaning the root is null, the output should be 0. If the tree contains only the root node, then the output is 1. For a full tree, where all levels are completely filled, the total number of nodes will follow the formula 2 to the power of h minus 1, where h is the height of the tree. Finally, if the last level is only partially filled, you must ensure that nodes are counted sequentially from the leftmost side. To solve the problem of counting nodes in a complete binary tree, the brute force approach is one option we can consider. The intuition here is straightforward: traverse every single node in the tree and count them one by one. This can be achieved using a simple depth-first search or breadth-first search algorithm. Starting from the root, you recursively or iteratively visit every child node and increment a counter for each node you encounter. While this method is simple to implement and easy to understand, it has a significant drawback. The time complexity is O(n), where n represents the total number of nodes in the tree. For very large trees, such as those with millions of nodes, this can become computationally expensive. Moreover, this approach doesn't take advantage of the special structure of complete binary trees, making it less efficient for this specific problem. Now, let's consider an optimized approach that fully leverages the unique properties of a complete binary tree. There are 2 key observations here. First, every level of a complete binary tree, except possibly the last, is entirely filled. Second, the nodes in the last level are filled from left to right without any gaps. These characteristics allow us to use the height of the tree as a crucial clue. For instance, the total number of nodes in a perfect binary tree of height h is 2 to the power of h1. Instead of traversing the entire tree, we can use binary search to efficiently count the nodes in the last level. Here's how: first, compute the height of the tree. Then, perform a binary search to determine how many nodes exist in the last level. Finally, combine this count with the number of nodes in the complete upper levels, which is 2 h1, 1. This method dramatically reduces the computational effort, as calculating the height takes O log n, and each binary search step also takes O log n. Since the height of the tree is log n, the overall time complexity becomes O log n, 2. While this approach is more complex to implement than brute force, it is far more efficient, especially for large trees. The optimized approach is the chosen strategy for solving this problem. Its efficiency makes it the clear winner, as it is significantly faster than the brute force approach. Instead of traversing all nodes, which takes O(n), we only perform a logarithmic number of binary search steps, resulting in a time complexity of O log n, 2. This makes the optimized method scalable and computationally feasible, even for trees with millions of nodes. By leveraging the unique structure of complete binary trees, specifically their height and the arrangement of nodes, we minimize unnecessary work, making the process highly efficient. While the implementation is more complex compared to simpler methods like brute force, the trade-off is worthwhile given the substantial performance gains. Simpler alternatives, such as iterative DFS or BFS, offer no advantage in terms of time complexity and were therefore not chosen. In conclusion, the optimized binary search approach is the most effective solution, combining efficiency with scalability to handle even the largest trees with ease. To begin counting the nodes in a complete binary tree, the first step is initialization. Here, the goal is to set up the foundation for the traversal process. We start by initializing a counter variable, count, to 0. This variable will keep track of the total number of nodes we visit during the traversal. Next, we prepare a data structure to manage the nodes that need to be processed. Depending on whether we're using depth-first search, DFS, or breadth-first search, BFS, this can be a stack or a queue. The root node is added to this structure so that traversal can commence. However, before proceeding further, it's crucial to check if the tree is empty. If the root node is null, this means there are no nodes in the tree, and we can immediately return the count as 0. With this setup complete, we're ready to start traversing the tree. Once initialization is complete, the algorithm moves into the traversal step. The goal here is to visit each node in the tree exactly once while updating the count. This is done by repeatedly processing nodes from the stack or queue until it is empty. For each iteration, the current node is removed from the stack or queue, and the count variable is incremented to reflect that we've visited this node. If the current node has children, such as left or right child nodes, they are added to the stack or queue for future processing. This ensures that all nodes in the tree are accounted for. When the stack or queue becomes empty, it indicates that every node has been visited. At this point, the algorithm terminates, and the value of count is returned as the total number of nodes in the tree. A few key insights help us understand why this approach works. First, to accurately count all nodes, every single node must be visited, which makes systematic traversal essential. Both DFS and BFS provide reliable methods for ensuring this. In terms of time complexity, the algorithm processes each node exactly once, resulting in an O(n) complexity, where n is the number of nodes in the tree. For space complexity, DFS typically has an O(h) complexity, where h is the height of the tree, due to the stack or recursion. BFS, on the other hand, has an O(w) complexity, where w is the maximum width of the tree, as it uses a queue. The choice of data structure plays a significant role in the traversal method. For depth-first search, a stack is used to track nodes that need to be visited, and nodes are processed in a last-in, first-out order. This approach is especially useful for exploring one branch of the tree deeply before moving to another. For breadth-first search, a queue is used instead. Here, nodes are processed in a first-in, first-out order, which allows for level-by-level traversal of the tree. Regardless of the method used, the algorithm must also account for edge cases. For instance, if the tree is empty and the root is null, the algorithm should return 0 immediately without further processing. In the case of a single-node tree, where only the root exists, the algorithm should correctly return 1. For skewed trees, where all nodes are either left or right children, it's important to manage the long chain-like structure efficiently, especially in DFS, to avoid exceeding memory limits. Finally, for a balanced tree, the algorithm should navigate all levels evenly without bias toward the left or right children. Let's consider an example to see how the algorithm processes a tree. Imagine a tree with the following structure. The root node is 1, which has 2 children, nodes 2 and 3. Node 2 further has 2 children, nodes 4 and 5. Using depth-first search, we start with the root node, 1, and increment the count to 1. Next, we add its children, nodes 2 and 3, to the stack. We then process node 3, incrementing the count to 2. Since node 3 has no children, we move to the next node in the stack, which is node 2. Processing node 2 increments the count to 3, and we add its children, nodes 4 and 5, to the stack. Finally, we process nodes 5 and 4, incrementing the count to 4 and 5, respectively. At this point, the stack is empty, and the algorithm returns the count, which is 5. Now, let's look at the same example but with breadth-first search. Starting with the root node, 1, we increment the count to 1 and add its children, nodes 2 and 3, to the queue. Next, we process node 2, incrementing the count to 2, and add its children, nodes 4 and 5, to the queue. We then process node 3, incrementing the count to 3. Since node 3 has no children, we move on to nodes 4 and 5. Processing these nodes increments the count to 4 and 5, respectively. Once the queue is empty, the algorithm concludes and returns the count as 5. Both methods, DFS and BFS, successfully traverse the entire tree and accurately count all nodes, demonstrating the robustness of this approach for solving the problem. This implementation efficiently counts nodes in a complete binary tree by leveraging its structural properties. A complete binary tree is a tree where all levels are fully filled except possibly the last, which is filled from left to right. The countNodes function starts by checking if the input root is null. If so, it directly returns 0, as there are no nodes to count. Otherwise, it calculates the depth of the leftmost and rightmost paths of the tree using the helper method getDepth. This method traverses either the left or right children of the tree until it reaches a leaf node, incrementing the depth counter at each step. If the depths of the leftmost and rightmost paths are equal, the tree is a perfect binary tree. In this case, the total number of nodes can be directly calculated using the formula 1 left_depth 1, which is equivalent to 2*depth 1. This is because a perfect binary tree with depth d has exactly 2*d1 nodes. If the depths are not equal, the tree is not perfect, and we need to count the nodes recursively. The function returns 1 plus self.countNodes, root.left, plus self.countNodes, root.right, where 1 accounts for the current root node, and the recursive calls count the nodes in the left and right subtrees. The overall time complexity of this approach is O log n, 2. Calculating the depth of the tree takes O log n, and in the worst case, we may need to calculate depths for O log n levels of the tree. This makes the solution highly efficient for large trees. Here we have the Java implementation for counting the nodes in a complete binary tree. The main method, countNodes, begins by checking if the root is null. If it is, we simply return 0 since there are no nodes to count. Next, we calculate the depth of the left and right subtrees using a helper method called getDepth. This method traverses either the left or right subtree depending on the Boolean flag passed. Once we have the depths, we check if the left and right depths are equal. If they are, it means the tree is a perfect binary tree, and we can directly calculate the total number of nodes using the formula 2*depth 1, which is implemented here as 1 leftDepth 1 for efficiency. If the depths are not equal, the tree is not perfect, so we use recursion to count the nodes in the left and right subtrees, adding 1 for the current root node. This slide defines the treeNode class, which serves as the basic building block for our binary tree. Each treeNode object has 3 attributes, an integer value stored in val, and 2 references to its left and right child nodes. The class also provides 3 constructors, a default constructor, a constructor that initializes the value of the node, and a third constructor that initializes the value along with its left and right child nodes. This structure allows us to represent the tree and perform operations like counting nodes effectively. Together, the solution in treeNode classes work seamlessly to handle the problem of counting nodes in a complete binary tree. The goal of this problem is to count the number of nodes in a complete binary tree. A complete binary tree is structured so that every level is entirely filled except possibly the last, which is filled from left to right. To solve this efficiently, we take advantage of the properties of complete binary trees. Specifically, if the left and right subtrees of a node have the same depth, the tree is a perfect binary tree. For perfect binary trees, we can calculate the total number of nodes directly using the formula 2 to the power of the depth minus 1. However, if the depths differ, it means the tree is not perfect, and we need to recursively count the nodes in the left and right subtrees. For instance, in the first example, we are given a perfect binary tree where the root has a value of 1, and all levels are fully populated. Let's see how we calculate the total nodes in this case. To begin, we calculate the depth of the leftmost path using the getDepth function with the left flag set to true. Starting from the root, we follow the left child nodes until we reach a null node, resulting in a depth of 3. Similarly, we calculate the depth of the rightmost path by following the right child nodes, which also gives us a depth of 3. Since both depths are equal, we know the tree is perfect, and we can use the formula 2 to the power of the depth minus 1 to compute the total nodes. Here, 2 cubed minus 1 equals 7. Therefore, the output for this example is 7. In the next example, the tree is no longer perfect, as the last level is not completely filled. In the second example, we start again by calculating the left and right depths from the root. The leftmost path gives us a depth of 3, and the rightmost path also gives us a depth of 3. Since the depths are the same, we know the tree is not perfect, and we need to recurse into both the left and right subtrees. For the left subtree rooted at node 2, we calculate the left and right depths once more, both of which return 2. This subtree is perfect, so we calculate its total nodes as 2 squared minus 1, which equals 3. Next, we move to the right subtree rooted at node 3. Here, the left depth is 2, but the right depth is 1, indicating the subtree is not perfect. We recurse further into its children. The left child of node 3 is node 6, where both the left and right depths are 1, so this subtree contains exactly one node. Adding these results together, we calculate the total number of nodes in the tree as 6. In the final example, we are given a tree with only a single node, the root. For this tree, both the left and right depths are 1. Since the depths are equal, the tree is a perfect binary tree. Using the formula for perfect binary trees, 2 to the power of the depth minus 1, we calculate the total nodes as 1. This makes sense since there is only one node in the tree. Thus, the output for this example is 1. To analyze the time complexity of the countNodes function, we start by breaking down its main operations. First, the getDepth function is used to calculate the depth of the tree. Since it traverses either the leftmost or rightmost path, the number of steps it takes is proportional to the height of the tree, which is h equals log_2, n, in a complete binary tree with n nodes. This makes the cost of each call to getDepth O, h. Next, at each node, the depths of the left and right subtrees are compared to check if the tree is perfect. Since this involves 2 calls to getDepth, the cost per node for this comparison is also O, h. Finally, if the tree is not perfect, the function recursively counts the nodes in the left and right subtrees. In the worst case, these recursive calls can continue down to the leaf level, resulting in a logarithmic number of recursive levels. These components together form the foundation for analyzing the overall time complexity. The overall time complexity of the algorithm can be expressed using the recurrence relation t, n, equals 2t, n/2, plus O, log, n. This accounts for the recursive calls to both subtrees and the depth calculations. Using the master theorem, this simplifies to t, n, equals O, log_2, n, which is the time complexity of the countNodes function. Now, for space complexity, the primary consideration is the recursive stack space. Since the maximum depth of recursion corresponds to the height of the tree, which is h equals log_2, n, the recursion stack requires O, h, space. Additionally, the algorithm does not use any extra data structures, so the additional memory usage is negligible. Combining these, the overall space complexity is O, log, n, dominated by the recursion stack. To put this into perspective, let's compare the time complexities of different approaches. A brute force approach would involve traversing every node in the tree to count them, which results in a time complexity of O, n. In contrast, the optimized approach used in the countNodes function leverages the properties of a complete binary tree, such as its structure and depth, to avoid traversing all nodes. This optimization reduces the time complexity to O, log_2, n, by focusing on logarithmic depth calculations and recursive calls instead of visiting every node. This comparison highlights the significant efficiency gains achieved by the optimized method. Now, let's consider the best, average, and worst-case scenarios for this algorithm. In the best case, the tree is a perfect binary tree. Here, the function computes the depths once and immediately returns the result, achieving O, log, n, time complexity. In the worst case, the tree is highly unbalanced, requiring recursive calls for both subtrees at each level. This leads to a time complexity of O, log_2, n. On average, the function performs logarithmic depth calculations and recursive calls, resulting in a time complexity of O, log_2, n, as well. This analysis provides a complete picture of how the count node's function performs under different conditions. When solving tree-related problems, there are some common mistakes to watch out for. First, overlooking edge cases can lead to incorrect or incomplete solutions. These edge cases include scenarios such as an empty tree, a single-node tree, or highly skewed trees that are completely unbalanced. Testing your code on these examples ensures robustness. Next, inefficient recursive calls can be problematic, especially in deep or unbalanced trees, as they may cause stack overflow. Optimizing recursion, such as by using tail recursion or switching to an iterative approach, can help mitigate this issue. Additionally, time complexity is critical. While a brute force solution might be clear at first, it can fail to scale for large inputs. For instance, a solution with n squared complexity becomes impractical when the number of nodes is very large. Furthermore, misunderstanding tree traversals, such as confusing pre-order with in-order or post-order, can result in applying the wrong approach and producing incorrect results. Finally, incorrect base cases in recursion can lead to infinite loops or flawed outputs. Always verify your base conditions to ensure your recursive logic terminates properly and handles all cases correctly. In interviews, there are key strategies to keep in mind when working with tree problems. First, clarifying the requirements is crucial. Ask questions such as whether the tree can be empty, if duplicate values are allowed, or whether the tree is strictly binary or more general like an n-ary tree. This ensures your solution aligns with the constraints of the problem. Another consideration is the choice between iterative and recursive approaches. While recursion is often more intuitive for tree problems, interviewers may prefer iterative solutions since they avoid stack overflow and demonstrate your ability to handle both methods. Optimal space usage is also important. For example, Morris traversal provides a way to perform in-order traversal without extra space by temporarily modifying the tree. Such techniques are valuable when space efficiency is a priority. Finally, recognizing common patterns is essential. Many tree problems use techniques like processing subtrees, divide-and-conquer strategies, or dynamic programming on trees, such as storing results at each node to prevent redundant calculations. Identifying these patterns can help you build effective and reusable solutions. Tree problems often share similarities with other problems, and practicing these related challenges can strengthen your understanding. For example, the problem binary tree in-order traversal, LeetCode 94, is a foundational exercise for mastering both recursive and iterative approaches in tree traversal. Another example is maximum depth of binary tree, LeetCode 104, which focuses on simple recursion and is an excellent starting point for beginners. The diameter of binary tree problem, LeetCode 543, introduces the concept of combining recursion with global variables, which is a common pattern in tree algorithms. Lastly, PathSum 2, LeetCode 113, demonstrates the combination of backtracking with tree traversal, offering a more advanced use case for solving complex tree-related problems. Practicing these problems helps you recognize recurring themes and develop a deeper understanding of tree algorithms. There are various approaches to solving tree problems, each with its own trade-offs. A brute force approach is often simple and straightforward to implement, but it may not scale well for large trees due to its inefficient n squared, or worse complexity. On the other hand, recursive divide-and-conquer methods are elegant and concise, making them a popular choice for tree problems. However, they can be memory-intensive because of the recursion stack, especially in deep trees. Iterative solutions avoid the issue of stack overflow and are a safer choice for handling deep trees, but they often require more complex logic and manual stack simulation, which can be harder to implement correctly. Another alternative is Morris traversal, which is a clever technique to achieve in-order traversal without extra space. It temporarily modifies the tree structure to avoid using additional memory, but this modification may not be acceptable in scenarios where the original tree must remain intact. Understanding these approaches and their trade-offs will help you choose the right solution for a given problem. To wrap up, we reviewed the problem of counting nodes in a complete binary tree. We discussed both brute force and optimized approaches, highlighting how leveraging tree properties can save computation time. Remember to practice similar problems to strengthen your skills. Thank you for watching, and don't forget to like and subscribe for more tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!